Hey, welcome to part 2 of my first OrCad project, the boosted flashlight. In today's video, I'm going to be covering boost converter theory, or at least my understanding of it. One thing I should probably mention with all my projects and everything I do on this channel, I'm not an expert at any of these things, and what I'm going to be presenting to you is my understanding of how these things work and on how to get things to work. And I can't promise you that I'll know everything that's going to be involved with any of these things, but I can promise you that I won't present to you anything that I wasn't able to get working. So hopefully whatever knowledge I'm able to give to you, or anything I'm able to show you, it'll work for you, and it'll just help you in your own research. So this is where I left off in my last video, and basically I had outlined um, what the boost circuit's going to be that's going to help us get that it's going to help me get my 3-volt input from 2 AA batteries up to 30 volts in order to power 8 lighting LEDs. And that's this boost circuit here, which consists of an inductor, a diode, a MOSFET, and a capacitor. In the last video, I tried to make an analogy or a metaphor between a swing set and the boost converter, and the whole premise behind that was if you had someone who was physically a lot smaller than somebody else. So in my example, I had a daughter trying to lift her dad to 5 feet in the air. How could she do it? Well, if she had a swing set, she could push him and get him up to 5 feet if she just pushed him again and again and again. And what is it about the swing set that actually allows her to get her dad up to 5 feet? Is it, is it just, does it multiply her strength by some means or something like that? No. What actually does the swing set help her do? Or how does it work? How does it help her get him to 5 feet? What it's doing is it allows her to use her force in cooperation with his own momentum. It's a combination of her applying pulses at the right amount of time. She only has to apply her force, the small force that she can apply. If she applies it at the right time in unison with his momentum, then she'll get him to 5 feet. And so that's the key. It's the momentum of her dad that allows her to get him to 5 feet, and the swing set just enables her to use that momentum. So how could we get momentum into our circuit? What is an electrical form of momentum? Well, I'm going to make the argument that an inductor will do that in the case of a boost converter. I'm briefly going to go into what an inductor is and how they work. So what is an inductor exactly? Well, let's look at just a property of electricity and electromagnetism. If you have a wire and you run a current through it, so here I've got the wire in black and my current's going to the right in orange. If you run a current through a wire, changes in that current will cause a magnetic field to form. Or, well, actually just the fact that the current's flowing causes a magnetic field to be created around the wire. This can be demonstrated if you run current through a wire and you bring a compass near it. The needle will point in some direction, like the wire with the current running through it will alter the normal operation of the compass, which is a cool thing to know, like to see in real life. But for simplicity's sake, I've tried to outline what happens in this diagram, and basically you need to use the right hand rule to know what direction the magnetic field's going. And if you don't know what the right hand rule is, I encourage you to wiki it or Google it. It's fairly straightforward. Basically, you point your thumb in the direction of the current, and whatever direction your fingers curl on your right hand, you have to use right hand for this. That's the direction of the magnetic field. So in our case, if our thumb was pointing to the right, our fingers would naturally curve like around the back of the wire. So that's why this purple arrow is going behind these things, and then down in front of it. I hope that makes sense, but if it doesn't, don't worry. That's not too important to understanding how the boost converter is going to work. But basically, if you run a current through a wire, it develops a magnetic field. And here I've drawn a simple inductor. And what it consists of is a magnetic core. So like the fancy word for this is a ferromagnetic toroid. And all that means is this is a chunk of metal that can be magnetized or that is magnetized. So usually this is something like iron. That's a really good magnetic metal. And then what you do to make it an inductor is you wrap wire around it. And the more times you wrap it around, the more inductance you'll get and things like that. But for simplicity's sake, you just wrap your wire around this around a magnetic donut essentially in the same direction, so that if current flows in through this direction, it'll go kind of like down in front, and then it's going to go behind, and then it's going to come back on this one in front and behind, and then down through this in the same direction. And as long as all the turns and wrappings that you do around this core in the same direction, they all add up, and it creates a magnetic field that's going to go through the magnetic or the magnetic core. And the reason you use a magnetic core is to help that magnetic field like keep within the core, so you don't lose as much energy to the environment. And it also helps like redirect it with the wire. So this is basically how you build an inductor. And let's see. So and what that gives you in terms of the properties of an inductor, what does it actually do? It's a pretty cool little element. And for just like some wrapping of wire in a magnetic core, you get a really cool property, and that is the voltage. Like voltage on an inductor, so V sub L, is equal to L times di dt. And what the heck does that mean? I know when I first started out looking at all these things, the mathematics drove me nuts. Like, you have to learn what each individual variable in the equations are and what their names are and what they mean to really understand it. So I've tried to break it down to you here. And this is the sentence that I would use to describe this equation. And it's basically that the voltage across an inductor equals the magnitude of its inductance times the change in its current over a given amount of time. So the voltage across an inductor, so if you drew it out, it'd be like plus minus or whichever direction the current's going, is equal to the magnitude of its inductance, so that's this L value, times the change in its current, so di dt, that's delta I. Hopefully, if you've taken some calculus or things like that, you'll be familiar with delta. But all delta means is you have like an initial current and a final current, and you subtract the initial from the final to get the difference between them. So that's all this d means, is it's the difference between the beginning and the end of it. Beginning and end of what? And that's the beginning and end of the period of time you're looking at it over. So the voltage across an inductor equals the magnitude of its inductance times its change in current over a given amount of time. Now this gives you some pretty unique properties. For example, if you just hook an inductor up to a battery, so let's say I had a battery up here and I just connected it directly from one end of the inductor to the battery down to the other. At first, the inductor, it's gonna generate a big voltage across it because it initially had zero current. So when I try to push current through it, that's a big change in current. But over time, as current starts to slowly build up in this thing and create a magnetic field, it's going to look more and more like a short, and eventually this just looks like a wire to the battery, and it acts like a short, and you'll burn out your battery or burn out the wire, whichever happens first. So, interesting property of an inductor. One thing I wanted to note with this, I'm really trying to bring that analogy of that the inductance is kind of like the momentum of this circuit. It's the thing that, like, I can apply small pulses with my 3-volt battery to you to build up your momentum, and your momentum is what's going to is going to help me get to that 30 volts in the end. And so, like, the thing to note here is, if you look at this equation, if you've taken physics, this might look familiar. It's F equals m times dv dt. If you remember, dv dt is the change in velocity divided by the change in time. In other words, that's acceleration. So this equation is force equals ma, or mass times acceleration. But if you look at it in this context, I think it makes a lot more sense that your mass is essentially your inductance. And as we know, a person's momentum is related to their mass. It takes a lot more force to stop a car than to stop a ping pong ball, because there's a lot more mass with the car than the ping pong ball. And you'll notice as you study like all kinds of things, if you study thermodynamics and electronics, physics, you'll notice that a lot of these equations, like the voltage on an inductor, is going to be very similar to the force on an object. And what they call those are analog equations. So there's a lot of times where you'll hear something called an electromechanical analog. And what that is you can describe a mechanical system, so maybe like a lever or something, with an equation that applies to a circuit and vice versa. And it's one of those really cool things about science and about nature, that the same kind of equations that govern one thing, like electricity, often govern other things like physical mass, or just the physical properties of the world and of the universe. And that's really cool. And it's these equations that build up the laws of the universe and how things interact, and I really find that interesting. And it's those kinds of things, like for example, that this inductor kind of acts like mass. It gives me the ability for my circuit to have momentum that enables me to create 30 volts out of 3 volts, and that's really cool. And one of my favorite quotes by Michael Faraday is something along the lines of, "Nothing is too wonderful to be true if it's consistent with the laws of nature." And I think it's pretty amazing and pretty wonderful that you can use just simple passive elements like an inductor to create 30 volts out of 3 volts. So let's get into that a little bit. So with this inductor, in my metaphor, I've given my circuit some inductance or some momentum. I've given it inductance, which I'm equating to momentum. And so how does that help me get to 30 volts? Well, let's say I had some current flowing through this inductor, and what that does is it builds up this magnetic field. Essentially, it's storing energy in the form of a magnetic field, and it's that stored energy that acts like the momentum, because just like if I get a mass moving, I'm storing kinetic energy. By getting a current flowing, I'm storing a magnetic field. I'm storing the momentum of the current in the form of a magnetic field. Excuse me. And due to the property of an inductor, what happens if I change that current all of a sudden? What happens if I told you, if I somehow stopped the current or redirected it in a way that makes it want to change instantaneously or over a certain amount of time? Well, I'm going to develop a voltage on my inductor, since my voltage is equal to the inductance times the change in current divided by the amount of time that change occurs in. So here, let's say I had some current flowing through my inductor, so I had stored up this energy in the form of a magnetic field, and then I try to change that current. Well, what's going to happen is I'll develop a voltage across that inductor. And if I changed that current in the right way, I could get that voltage across the inductor to be in the same direction as my input source. So all of a sudden, I have my initial input of 3 volts, and since it's in the same direction as the voltage on the inductor, they add together to give me something larger than the input. So here, the equation becomes 3 volts plus the voltage on my inductor is going to equal 30 volts. So it's that property of the inductor, that the voltage on the inductor equals the magnitude of the inductance times the change in current over a given amount of time. That physical property of the inductor is what's going to allow me to create a voltage using that inductor larger than my input. So really cool. But in order to do that, I have to change that current. I need that DI part of the equation. How can I do that? Well, that change is going to come from these two elements here, and they work cooperatively together in order to allow this circuit to do that. The main important one is this NMOS. If you're not familiar with an NMOS or an N-channel MOSFET, they are, what's the word? I think the most ubiquitous circuit element used today probably. They make up a large portion of all your processors and everything you use. But in this circuit, we're mainly just using the NMOS as a simple switch. So it's something that can turn on and off. In other words, I can make this connection short to ground, or I can leave it open so no current can flow down this branch of the circuit. Now the diode, hopefully you're familiar with diodes. They're a really simple circuit element that just allows current to flow this way from left to right, but it won't allow current to flow from right to left. So I'll go into that as we keep going, but just keep that in mind. So let's say we wanted to store up that magnetic field in this inductor. So I want some current to flow through that guy. One way I can do that is by shorting this NMOS to ground. So if I turn this on, if it's a switch, and I turn it on and I connect this wire straight to ground, I get a nice loop here where my battery's just connected to my magnetic field and it goes right to ground, so I get that nice current flow. And thanks to my diode, no current's going to flow from all this stuff over here back into this circuit. So essentially it isolates it. So that's why I left this here. The diode's blocking, so it essentially isolates my output, load, and my capacitor from this circuit. And then my NMOS is closed, so it basically shorts to ground, and that enables my battery to just focus on charging up my magnetic field in my inductor. And so here in this part, I'm just charging that inductor and building up momentum. Okay, and then next, let's say I open this guy then. So I've stored up a magnetic field now, and then I'm going to open this section. I'm going to break this wire with that NMOS by turning it back off. And what that's going to do is it's going to create that voltage on this guy, because what happens is, since this opens up, if no current flows anywhere else, then I have a huge change in current, because where I had a good constant current flowing here before, now it gets shut off and it says, hey, you can't flow. But the inductor can't allow that. It's going to create whatever voltage, it needs to enable that magnetic field to keep flowing. It's got that momentum, it's got all that energy stored in a magnetic field. And that magnetic field is going to create a voltage on the inductor in however large it needs to allow that current to keep flowing. It just wants to keep the current flowing. It's got momentum. And so it creates this V sub L, or my inductor voltage, in such a manner that all of a sudden I get a larger voltage out thanks to that input voltage being added to the inductor. So I get something like 30 volts on the output, because it needs to let that current keep flowing, and it's going to push it to store up this capacitor. That's one thing I forgot to mention on this previous slide, was if I did have some energy stored in this capacitor, it would allow the rest of this circuit to keep working even though it is isolated from this guy, as long as that charge is sufficient to keep this going. And so here I'm having my inductor store up that capacitor a little bit again, but also feed all of these LEDs, keep pushing that current through the circuit. And so hopefully that demonstrated that by switching this NMOS on and off, I can, in one part of time, I charge up my inductor, I create a magnetic field, and then when I open it, that stored energy, that stored momentum, electrical momentum, is going to say, hey, I want to keep the current going. So I'm going to create a voltage on my inductor in such a manner that it's going to allow that current to keep flowing, and that's going to boost this to 30 volts and let everything keep going. And then also charge up the capacitor. But in order to do that, I need to turn that NMOS on for a certain amount of time in order to charge up my inductor, and then I need to turn it off for a certain amount of time to charge up my capacitor with the energy that I stored, and also to feed all these LEDs while I'm charging up that capacitor. I hope that makes sense. And how we do that is with pulse width modulation. And now I'm going to get into deriving how we can calculate, how we know the timing to switch this guy on and off. Because, you know, how long do I let this guy charge for, and then how long do I let it dissipate its stored energy into the other circuit elements. Let's look at a simple derivation, and that again, this is all going to tie back into the property of an inductor, which is the voltage on the inductor is equal to the magnitude of its inductance times the change in its current over the change in time over a given amount of time. Okay, so let's look at the amount of time that the switch is closed and I'm charging up. Here's that original equation. That's the property of the inductor. I've relabeled it in this next step just to demonstrate that I'm turning that switch on, so that's my time on, for a certain amount of time, and I'm changing the current by a certain amount in that time. So here I have the change in my current while the transistor's on, that's why it's DI on, divided by the time that the transistor's on. So the voltage on the inductor generated is going to be equal to its inductance times the change in current while that NMOS is on, divided by the time that it's on. And you can rearrange this equation in order to give you the change in current while the inductor is on. I hope that makes sense. This is just relabeling it to get to this step, and then this is rearranging it to solve for the change in current while it's on over that given amount of time. And the reason I have put it into this form should become clear in a second. Here's the second half of the circuit's performance, and in this half I've got that NMOS open, so that branch to ground is broken and all my energy has to come this way. And in this time, here's that same initial property of the inductor. I've relabeled it because now the voltage on the inductor can be written in terms of the voltage out and the voltage in. So since this guy is in parallel with both of these, you could really say that V out is equal to V in plus VL, and so VL is essentially equal to V out minus V in. That's where the first half of this equation comes from. And the second half is obviously the inductance. That doesn't change as long as you don't switch out inductors. And here it's just the change in current while this thing's off. So how much current am I sending out of that stored magnetic field into the capacitor and in through all these LEDs over the amount of time that I leave that switch off. And then I'm going to take this equation and you can rearrange it to solve for the change in current while that switch is off in terms of the time that it's off. So the reason I solved both those equations or rearranged for those two settings is there are a couple different modes you can run a boost converter in. In this series or in this project, I'm only going to be talking about continuous mode operation. Honestly, power electronics is something you could dedicate your whole life to, and obviously I'm not experienced enough to get into any kind of depth on these subjects. I just want to have and demonstrate a practical understanding of these things so you can use them in simple circuits, and so I can use them in simple circuits. And so here I'm only going to be looking at continuous mode operation of a boost converter, and what that means is there's always energy left over in that inductor between cycles, or there's always at least some energy. And so what I mean by that is I never deplete this guy. I've stored up a magnetic field in the inductor, and even though I tell it to let me think, even though I send the energy out while that switch is off, I'm using the stored energy to charge the capacitor and to run these LEDs. I get my timing in such a way that this guy never gets fully depleted. I always want a little bit left over in here, and that's what continuous means. There's always current flowing through this guy. And so I've put the quote here. This is how I would say it. In continuous mode operation, there is always energy stored in the inductor. So in other words, there is always current flowing through the inductor. It always still has that built up magnetic field energy storage, so it always still has momentum left over in it. So in order for this condition to be true, this first statement has to be true. And what this means is the change in current in the inductor while it's on, while the switch is on, so the change in current while I'm charging this guy has to be equal to the change in current while it's off, while the switch is off. Sorry, I hope that's not getting confusing. And really all that means is the amount of energy I store when I charge the inductor just is equal to the amount of energy that I send out of the inductor when I deplete the inductor to charge the rest of the circuit. So the energy I store in the inductor is equal to the energy that I use in the inductor when the switch is off. And since this equation is true, 0 amps is on the right. So I just rearranged this to say that the change in current while I'm charging is going to be, while I'm charging the inductor, is equal to the amount of the change in current when I'm utilizing the inductor, the stored energy in the inductor. So these are the two equations that I derived before for the change in current when the MOSFET's on and the change in current when the MOSFET's off. And rearranging all of this, you can get a nice, pretty simple equation down here where the voltage out is going to be equal to the voltage in only in terms of the amount of time I leave it on and the amount of time I leave it off, the switch, the NMOS. And that's a beautiful equation because you'll notice here that there's no reference to the frequency that I'm changing that MOSFET on and off. It's just the amount of time that I leave it on versus the amount of time that I leave it off. The output voltage is directly related to that. If you read the Wikipedia article on boost converters, and if you read power electronics books, you'll often find that this equation in this form. And all that they've done is they've defined this time, this T on divided by T on plus T off is the duty cycle of the waveform. Duty cycle is something you should know if you ever want to use pulse width modulation or if you're going to get into power electronics, something like that. It's really simple. It's just the ratio of the amount of time that you have an on signal divided by the total time that the signal takes, or the period of the pulse width modulation signal. So here I've drawn a couple different waveforms. This is a duty cycle of 20%. So you can see that it's on for about 1/5 of the amount of time that it's off. Here's 50%, so it's on 50%, off 50%. And here it's a duty cycle of 80%, so it's on 80% of the time, off 20% of the time. That's all duty cycle means, and it allows you to write that equation in a very simple form where the output voltage is just related to the input voltage and the duty cycle of your timing waveform that you put on the MOSFET to switch it. So here what is the duty cycle we're going to need for what I wanted to accomplish in this project? I wanted an output voltage of 30 volts given an input voltage of 3 volts from 2 AA batteries. So using that equation, we have V out equals V in times 1 divided by 1 minus the duty cycle. You can rearrange this equation to give you duty in terms of V in divided by V out. So it's just 1 minus that ratio. So I do 1 minus 3 divided by 30, and that gives you a duty cycle of 0.9. In other words, you have a 90% duty cycle. And so the timing waveform should look something like this. It's on 90% of the time, off 10% of the time. That's what I need to give that NMOS back here, that pulse width modulation, a duty cycle of 90%. I need to turn it on for 90% of the time, off for 10% of the time in order to boost 3 volts to 30 volts. I'm worried that this is a lengthy video. I haven't checked the time. And so I'm going to stop it here, and in the next video we're going to be actually drawing and simulating this circuit in OrCad, and hopefully things will make sense when you get to see the output waveforms. But I hope this has been some help to you, and hopefully you enjoyed it. Thanks for watching.